Great, thanks. And yeah, so I want to get to saying something about this sort of major result of Toan and Vauquier from several years ago about the sort of representability of moduli of objects of DG categories. And to get there, first, I need to say something about like what is a derived scheme, maybe, what is a derived stack, and so forth. So to start, we're going to talk about derived stacks. And I'm not going to go straight there. Don't worry. I'll have a little bit of orientation. So K is going to be a fixed simplicial commutative ring in the sense that we talked about last time. And I want to say a little bit about the sort of homotopy theory of simplicial commutative K algebras. This is kind of what's going to be our coordinate functions for derived affine schemes. And so I wanted to just make a few remarks about the structure of this as a sort of as a homotopy theory, or really as an infinity category. So what does it mean to say, so, we'll be hearing from Carlos Simpson later about infinity categories. There's, I really am thinking about this as an infinity category, and all that I want you to take away from that during this lecture is the fact that if I have two objects in here, if I fix two objects that are simplicial commutative K algebras, then I don't just have a set of homomorphisms from one to the other. I have a space, which will always be the mapping space of K algebra maps from R to S. And so this is really a topological space, and this behaves well with respect to equivalence. So if I replaced S by an equivalent simplicial commutative ring, the homotopy type of this mapping space wouldn't change. Okay? So this is the kind of thing that we're going to use when we say that that this is an infinity category. So let me just give a couple quick examples here. So first of all, if I take the mapping space from K itself to S, well, K is the initial object. So think about the integers. There's only one commutative ring map from the integers to another commutative ring. And so this is a single point. This is a contractible space. So when I write this symbol, I always mean weakly equivalent. Or equivalent as homotopy theories or something like that. And if I write this, I'll mean isomorphic in some one category. Okay? So I have this mapping spaces, and let me just do one other sort of simple example. If I take maps in this homotopy category, from now let's take K and let's adjoin a variable in degree 0, so the free simplicial commutative ring on a degree 0 class, and I take the maps from that to S. Well, just like in ordinary commutative ring theory, this gives me the underlying set of S. But this time, this is S viewed as a simplicial set, or equivalently as a topological space. And so we can see the homotopy groups from here. Okay? So this is just a little bit, I'm kind of just going to remind us about the lay of the land of this. And I just want you to kind of take it on faith that there's a good theory like this, or think about what we talked about last time, because this is really going to be the foundational object that we're going to use to build derived algebraic geometry. Okay, so this is one of the properties it has. We also had these cotangent complexes, not ample line bundles, but cotangent complexes here. Let's see. So I'm going to say that R inside a simplicial commutative K algebra is discrete. So this is a definition if pi I of R is 0 for I more than 0. Okay, so what we're seeing here is there's an underlying topological space or simplicial set for any simplicial commutative K algebra, so it makes sense to talk about its homotopy groups. I'm just going to say it's discrete if all of the positive ones actually vanish. And then what happens, there's a full subcategory. I'll just write K discrete sitting inside here. This sort of the whole homotopy theory of discrete simplicial commutative K algebras is equivalent to ordinary commutative algebras over pi 0 of K. So K was some simplicial commutative ring. Pi 0 is actually an ordinary commutative ring. This is just an ordinary category, and if we just focus our attention on the discrete simplicial commutative algebras, then we're just recovering ordinary commutative ring theory sitting inside here. And this is actually fully faithful. There's a left adjoint. This left adjoint is just take pi 0. Please? Exactly. That's exactly all they are. And it turns out, let me just remind you that pi star r was a graded ring, graded commutative ring, where we have this kind of rule for commutativity. If x and y have degrees given by x and y, then this is true. And then furthermore, odd degree elements square to 0. Okay, so this is the structure that we get on those homotopy groups. Because they're all abelian groups. I mean, in particular, they're all abelian groups. Okay, so this, what? This is pi 0k, yeah. No, I'm just saying that this is a full subcategory of these, of the discrete commutative rings. So K itself might not be an objective here, but I'm just writing down some sub-objects, some class of objects here. No, I think for simplicial commutative rings, it actually turns out that x squared is 0. This is what I wanted to say. But right, so for a generally infinity thing, what you're thinking, we wouldn't have this, but for simplicial commutative, it turns out that this is the case. Thanks. So finally, I just wanted to say that, let's see, R, so if I have a simplicial commutative K algebra R, this is locally of finite presentation. If what? Well, if R is inside the full subcategory of compact objects, and I'll define what this means in just a second. So this is an omega, and these are the objects where if I take this mapping space, let's see, blank, this gives me a functor from simplicial commutative K algebras to simplicial sets, or to spaces. Let me just say spaces, the homotopy theory of spaces. And I want this functor to commute with filtered colimits. So this functor commutes with filtered colimits. So this is the exact, if you did this in the category of commutative algebras and you took you took Rham out of a commutative ring, then saying that that functor to sets commuted with filtered colimits would exactly be saying that the ring is finite presentation. Okay. Okay, so that's just a little bit of orientation to these to this category. And I can also take the derived tensor product of two of these things. There's notions of free commutative algebras like that are analogs of polynomial algebras. And I can do a lot of, most of the basic constructions of ring theory here. Okay, so I'm about to move towards the sort of putting a topology on this, but are there any questions? LFP, locally of finite presentation. Other questions? Okay. So I want to talk about étale maps. And so So the first definition is that K to R is formally étale. Well, you can guess the definition. So if L, the cotangent complex is 0. Okay, so that's just some class of maps. It's maybe not there are probably open questions about what sort of things are actually formally étale. And then K to R is étale if it's formally étale. So if, well, it is formally étale and, well, locally a finite presentation. This is probably somewhat familiar. So if we happen to be working with an ordinary commutative ring, then this would in particular apply to ordinary étale maps. And so there's an important fact here that there's a different description of étale maps. So K to R is étale. So that's equivalent to the following. So it's equivalent to being étale on pi 0. And this is just a map of commutative rings, okay? And the induced map, so from pi ik tensored over pi 0k with pi 0r to pi ir, this is to be an isomorphism. And since this map is étale, it's in particular flat, so there's no need to derive this bottom term. Okay? So these two things are equivalent. So this tells you something about what étale morphisms of simplicial commutative rings look like. Well, pi 0k to pi 0r is flat. Okay?
Is there a vectorial description of formally étale as in the Grothendieck definition?
Yeah, right. Right. So as we saw last time, the cotangent complex has a universal property in terms of mapping to square zero extensions, and so this vanishing in particular implies things about lifting over square zero extensions. Mm-hmm. Okay, so here's a major kind of theorem. Let me give like a little bit of attribution. I'm not doing a very good job of that, and I don't really plan to. But I don't know. So a lot of what I'm going to say today about DAG, it goes back to work of sort of Lurie, Simpson, Toen, Vauquier, Vitsotsi, and many, many other people. If I don't attribute something, it's probably to one of these people. But this stuff is basically by now foundational in the area. So this first theorem is that let's look at simplicial commutative K algebras that are étale over K. So all morphisms that are at K to R that are actually étale. So a priori, there are mapping spaces between objects here, right? If I have two étale K algebras, there's a mapping space. But it turns out that those mapping spaces are all discrete. And this is just equivalent to the ordinary category of étale pi 0k modules. Okay, so this is a kind of magical fact that I think helps guide a lot of the intuition about what's happening. It says that the small étale site of K is the same as the small étale site of pi 0k. Okay? Now let me make a remark that I think is very helpful for my intuition. So recall that there's topological invariance of the small étale site. So for example, let's now just say that R is an ordinary commutative ring, and I inside R is a nilpotent ideal. Then the base change map gives me an equivalence from the small étale algebras over R to étale algebras over R mod I. And there are more general statements one could make, but this is one of them. Sorry. Okay. So this topological invariance of the atoll site, I want you to think of the higher homotopy groups in the simplicial commutative ring as being nilpotents, higher nilpotents. And so in particular, and in some sense that's really true, any simplicial commutative ring has a map to pi 0k, and this is really some kind of pro-nilpotent extension. So pro-nilpotent extension, so what does that mean? Well, this factors through what I'm going to write tau less than or equal to nk. So this is a new simplicial commutative ring, and the properties it has is that the ith homotopy group of tau less than or equal to nk is, well, it's the ith homotopy group of k if 0 is less than or equal to I is less than or equal to n, and it's 0 otherwise. Okay? So let's think about this guy. Take a positive degree element. So if I take x in pi I of tau less than or equal to nk, where I is more than 0, well, what do I know? I know no matter what, x to the n, this has degree n times I, so it's outside of this range now. Or maybe I need to do, maybe I had better do n plus 1. And this is 0 in the homotopy ring. So all of the positive degree elements in this truncation, so this is called a truncation, are actually nilpotent in the homotopy ring. And the whole ring is, in fact, an inverse limit of these truncations, okay, as n gets bigger and bigger. And so this is the sense in which we're supposed to view this k as being a pro-nilpotent extension of pi 0k. And this fact about atoll k algebras is really an extension of, or you should think of it in the same vein as this topological invariance, or this nil invariance of the small atoll site. Okay, any questions about any of that? Okay, so it's time to do some derived algebraic geometry. We have this notion of, what? I was going to try this. I was motivated by Carl's talk, and we'll see how it goes. So these are going to be the derived affine. This is going to be the homotopy theory of, maybe I'll say affine derived schemes, affine derived schemes. And I think you all know what I'm going to say now. This category is just the opposite of the category we've been studying. Okay? And if I have an object here, then of course I'm just going to view spec R as the corresponding object here. And maps from spec R to spec S are going to be the same as ring maps from S to R, the usual thing. So this gives me this category, and I have a natural notion of a topology on it, just given by the atoll topology. So this turns this into some kind of site where we have. This is an atoll cover if sort of the induced maps pi 0 to pi R to pi 0 SI is an atoll cover in the classical sense. And so now I'm going to start to look at the category of sheaves we're going to study, and that's going to be the home for all of our geometric objects in our stacks. Yeah, so I mean, okay, so what's an example? Yes. So the question is, what's an example of a simplicial commutative ring? And, you know, the easiest one, okay, let's just take this. I think I said this last time. Let's let x go to 0 here, and instead of taking the ordinary tensor product, let's take the derived tensor product. So this is a ring. This is a simplicial commutative ring, and the homotopy groups are what? It's just k. It's the ordinary tensor product. Well, it's k if I is 0, and it's also k, but it's k in its instantiation as tor1 of kx. K with itself if I equals 1, and it's 0 for I more than 1. So that would be one example.
I usually think of the derived tensor product as a complex. So basically, you are saying that.
So right. So what we can do is, so I have k. I'm viewing k as a k algebra, as a kx algebra, and I can take one of these canonical resolutions. So I'll call that S dot. So this is now, in each degree, a polynomial ring over this. And it's a simplicial commutative ring. And when I say this, what I really mean is S dot tensor over kx with k just in each degree. And that's a new simplicial commutative ring. Good. Any other questions? Pardon me? Yeah, right. Yeah, sorry. Thank you. Absolutely. Good. So,
one more question. Continuing with this example, is there any hope of describing the topological space underlying that simplicial ring, or is it too complicated?
No, there absolutely is. Let me get to that in just 1 second. That was what I was going to say in just a moment. So I can now look at presheaves on here, and I'm going to sort of sweep under the rug some set theoretical technicalities. Okay, so you usually do the usual thing and look at things that have at most kappa or fewer than kappa generators or something like this. But okay, let's sweep this under the rug. So this presheaf category, what do I mean by this? This is just functors from derived affine schemes op to spaces. So these are sort of functors as homotopy theories or as infinity categories. And because, we know what this op is, this is just the same as covariant functors from simplicial commutative K algebras to spaces. And inside here, I'm interested in a category of étale sheaves, which this is going to be the real home for everything that we do. And the basic sort of defining property of one of these étale sheaves is that if R to S is an étale cover, so sort of because spec R is sort of quasi-compact, I can always refine any big cover to an actual map of affines. So if R to S is an étale cover, what I can build from this is a cosimplicial complex, typically called the Amatzer complex. Okay, so it looks like S tensor over R with S, and then 3 copies and so on. So this is just the 2 ways of including in the identity, but there's also a map back given by multiplication, which is R linear, and so forth. So this is a cosimplicial object in simplicial commutative rings. And the basic idea... Yeah, right. We're taking the check nerve, absolutely. So if we took the opposites, this would be the check nerve. And we basically want our sheaves to have the following property. So FR should map, so it maps to the limit over F of this diagram, so tensor dot plus 1. So this is the totalization, so it's a limit over the simplex category. And what we want is this to be an equivalence. So this is the full subcategory of presheaves for which, for every atoll cover, this natural map is an equivalence. So are you saying I should say f of, yeah, I mean, do I? I think this is enough, but maybe I'm being silly. The question is, do I also want to include something about finite products? But I think this is okay.
What's the exponent?
Dot plus 1. So like 0 plus 1, 1 plus 1, 2 plus 1. Okay.
That arrow is an equivalence?
Yeah, right. So there's always a natural map just from the diagram, and the sheaves are those for which, for every atoll cover, when we look at that arrow, we get an equivalence.
What sort of equivalence?
A weak equivalence. These are pre-sheaves of spaces. They take values in topological spaces. What?
Does it make it really hard to weak equivalence? I'm so used to actually constructing an object.
Yeah, so do I want to just say that f of like, yeah, okay. F of the empty set is a point. Yeah, right, I think, yeah, you're right. In this context, I should probably say that.
What is the role of this Amundsen complex? Is this a condition for being a sheaf?
It's a condition for being a sheaf. So for all atoll covers like this, construct the Amundsen complex, get this natural map, and require that it be an equivalence. This is like, right, you know, if you just looked at a small part of this diagram, this is the ordinary sheaf condition for sections, right? But because we have higher homotopy groups, we have to require more and more coherence.
You're just spelling out the definition of sheaf.
Yes, in this context. That's correct. Okay.
Sorry, I just one more small question, which is, if you have a finite presentation, guys, is it definitely just defined by a finite amount of data? Does that make sense somehow?
Yes. Specifically, it's a retract of a finite colimit of free algebras on, like, you know, small objects. Okay, so let's see. So this is the category that we're going to be interested in, and there's a Uneda functor, and it does turn out that it lands in this subcategory, and we will view spec R always as being in here. And now what we're going to do, I need one more definition, and then we're going to start talking about stacks. I just wanted to say what it means for a map to be smooth. So this is smooth, or if it is locally a finite presentation, and the cotangent complex L S over R, has Tor amplitude in 0, 0. So now's a good time to introduce what that means. So let me define what it means for an object to have Tor amplitude in 0, 0.
Hard field between the Uneda things are sheaves. In algebraic geometry, it's not trivial. I'm wondering what hard here follows.
No, this is a good question. I mean, in the end, what you prove, in the end, what you're asking is if I take the limit of this diagram in simplicial commutative rings, do I get R again? And that turns out to be true. So one proves that that is true. Yeah. And I mean, but I think in this case, you can even reduce to the classical statement in algebraic geometry. You can reduce to pi 0. OK. OK, so what does it mean? OK, so let's see. So suppose I have a simplicial commutative ring R. And now this has a derived category of R modules, which we haven't yet talked about. But more or less, this is going to be modules over R in the derived category of the integers. But we have to be sort of careful how we do this. Like, it's important to really view this as an infinity category or DG category. Or you can look at DG modules over R or something like that. Now, let's suppose I have P in here. So P is perfect. So I want to make two definitions. So definition. So one, P is perfect. Well, this is just, again, if it's compact. OK, if it is in the compact objects. So in other words, that says that taking maps out of it commutes with colimits. And the second thing I wanted to say, so P has Tor amplitude in some range A to B. If the following is true, if I take P and I base change down to pi 0 R, if this has Tor amplitude in A, B, and this is something studied well in SGA 6, what it means is that if I restrict this complex to any closed point of spec pi 0, or any point of pi 0 R, then I have homology concentrated in this range. So specifically, HI of P tensor over R, pi 0 R, tensored with any discrete pi 0 R module M. So this is actually in mod pi 0 R. So I do this tensor product. Everything is derived here. And this should be 0 for I not in the range A to B. That's the definition. Sorry. Reflexively just doing this. OK. Yes?
So in the definition of a smooth morphism, do you require the tensor complex to be perfect?
So the question is, if in the definition of a smooth morphism, do I require it to be perfect? Because of local finite presentation, that plus this does imply that it's perfect.
That's
0,
0, 0?
0. OK. So now let's build a gigantic world of derived stacks. And right. What time did I start this talk? Sorry. At 11. Great. OK. So now let's do derived stacks. So OK. So a morphism x to y, so f, in étale sheaves here is 0 geometric. So there's a bunch of different kind of conventions we could choose here. I'm choosing one just because it's simplest for the context of this talk. You might have your own favorite convention. That's OK. So it's 0 geometric if for every r point of y, so this is like being representable in the sort of functor of points perspective. So for every r point of y, when I take the pullback here, I'll call that P, I take the pullback in this homotopy theory or in this infinity category, what I ask is that this is actually a disjoint union of affine schemes for some index set I. Okay. This is like saying the pullback is a scheme. It's a slightly stronger statement. You could also ask for this to be some kind of algebraic space. You would end up getting the same class of geometric objects, but with slightly different end geometricities in the end. But yeah, if for all r points of y, this is true. You can present this pullback. You can write it say that it's equivalent to a coproduct of affines, of representables. Okay.
It's not true that disjoint union is itself spec product? Like that way?
No. Not in ordinary algebraic geometry either.
Your index set finite necessarily or
No. So a zero geometric morphism, the question, sorry, was, is the index set finite? The answer is no. So a zero geometric morphism is, let's see, locally a finite presentation if I can choose, well, if all of these SIs are locally a finite presentation over R. If, I'll just say it, if the SI are LFP over R. Okay, that's one, and it's smooth if the SI are smooth over R. Okay, so that defines us a notion of zero geometric morphisms, and now I'm going to define inductively a notion of n geometric morphisms for any n. So, okay, so definition. So x to y is n. So let's assume it's defined for n minus 1. So this is n geometric. So if, for all r points of y, when we're going to do the same thing, we're going to look at the pullback here. And now we're not going to quite ask for this to be a disjoint union of affines. Instead, what we're going to ask is for this to have a map like this, which is smooth, surjective, and n minus 1 geometric. So for all points of y, then there's some, what we can call such a thing an atlas, if we can find a smooth, surjective, n minus 1 geometric morphism here. And now I'm just going to transport these same definitions, LFP and smooth, to this context if these compositions are locally finite presentation or smooth. Okay?
What does surjective mean in this context?
Right. So surjective just means that sort of a tall locally, I can lift points. I can lift, yeah. If I take now like let's see, a T point of here, there's some a tall cover, spec W, where this point lifts through there. What am I doing here? Excuse me?
What's the intuition behind zero geometric?
Well, the idea is we're starting with a specific class of objects that we're declaring to be geometric. So here, okay, we have all étale sheaves. It's some huge category, but some are probably more interesting geometrically than others, right? So the first ones are just the representable ones. Those certainly should count as geometric. And what we're doing, so that's just going to be our basic building blocks. And so what this process does is it starts with affine schemes, and it builds some new geometric objects by taking quotients by smooth, I think of it as by taking quotients by smooth group actions. So I'll give an example here in a second. Now, you could replace this zero geometric with a notion of derived algebraic space, but that would require me to introduce derived algebraic space. And you would get a very similar class. It's just that a given geometric object might be n or n plus 1 geometric, depending on what you declare to be zero geometric. So this is just one choice.
So in classical terms, a scheme would be one geometric, not zero geometric.
Yeah, so somewhat, yeah. This is the simplest one, but it has the downside that in this, a non-affine scheme, it's going to be one geometric, typically, under this definition. C'est la vie. Pardon? Yeah, thank you. Yes, I'm going to ignore all separation and quasi-compactness issues in this talk, but that is very true. I don't assume my sheaves to be hypercomplete. But I believe that any n-geometric one will be hypercomplete, I think. So, because you're building it kind of in finitely many steps from something hypercomplete. So the question was about hypercompleteness, which is some technical thing that I don't want most of you to think about at the moment. Okay, so let me, I want to give, okay. Okay, so we just defined a huge class of objects. So maybe it's good to give an example here. So I'm going to write GL1, and this particular object is going to come up quite a bit next time. So GL1, this is going to be spec of k t plus or minus 1, where this is in degree 0. Okay? So, but I'm viewing this still as a simplicial commutative ring. So this represents some functor. And so what is GL1 of R? So this is so by definition, this is maps in simplicial commutative K algebras from K t plus or minus 1 to R. And what turns out that if I take the homotopy groups of this, well, in degree 0, I get the units in in pi 0 r, and in higher degrees, I just get pi I r. Okay. So this is important. I'm writing GL1 here as opposed to GLM. I'm writing GL1 as opposed to GM for the following reason. There's another functor, GM, of R, which just takes values in sets, which I can define to be pi 0 r units. And you can, as an exercise, this is an étale sheaf, but as an exercise, you can prove it's not geometric. This is not geometric. It's not n-geometric for any n. Okay? So there's kind of a big difference between these two objects in this setting, and this is a good sort of example for testing the intuition. So this is a 0 stack, obviously, because it's just representable. So this is a 0 geometric derived stack. Okay. So that's probably not the kind of example you wanted to see. K tensor K over Kx. Yeah, right. Okay, while we're here, let's go ahead and do that, just so I don't forget again. So let's do spec of K tensor over Kx with K. And the way to view these affine schemes is this really, there's a slightly different perspective where you can make rigorous the following idea. This is, so I'm going to put this in quotations, spec K, that's pi 0 of this, but with a different sheaf of rings. So it's this as a topological space, but with a different sheaf of commutative rings, this time with a sheaf of simplicial commutative rings. With O, a sheaf of simplicial commutative rings. Okay. So you can, this time spec K was probably kind of dumb. We could have done some more interesting version. Sort of in general, spec R, you want to view as being spec pi 0 R as a topological space, or the small étale site, but with a different sheaf of commutative rings on it, specifically this sheaf given by this simplicial commutative ring. And so if you have a standard open given by inverting some element f, what you apply to this is you take R and you invert 1 over F as a simplicial commutative ring. Okay, and so that gives you a different, it's like a higher homotopical version of the structure sheaf on the same underlying topological space. Okay, so now what I want to do is consider BGL1.
Were you going to show us the geometric realization of this little example? The canonical resolution, and then you said it was hope, that one could hope to understand.
No, I'm saying that if you want to view spec as a topological space, which you can do, it's just spec of pi 0. With a
not the spec of the ring, but rather the topological realization of this simplicial ring, along with its interesting pi i's that you told us about before.
okay.
Can that be described?
I mean, it's some space with homotopy groups k in degree 0 and k in degree 1. It may well be the homology, the k homology of S1, but I don't want to. Yeah, I don't want to make a bet right now. It is S1. Okay, even if k is not characteristic 0. Yeah. So from my perspective, it hasn't really generally turned out to be fruitful to think of these simplicial commutative rings as themselves being topological spaces and understanding the underlying topological space, except in as much as they have homotopy groups, they have this Postnikov tower that we wrote down, and you can sometimes understand obstruction theory in that way. But the actual specific topological spaces that you get out, I guess I just haven't really thought about them. Yes?
Usually, one thing I find very useful for intuition is not thinking of simplicial rings, but thinking of differential graded rings. And in that case, one can really write it down, generate its relations and so on. Could you comment on whether I was told by people I trust that in characteristic 0, I could work with differential graded instead of simplicial?
That's true. So the question is, can you work with differential graded instead of simplicial commutative in characteristic 0? The answer is yes. Yeah. I guess we discussed this yesterday. So anyway, so I wanted to give this example of an actual geometric stack that's not 0 geometric. And what is this? So this is the classifying stack of BGL1, and what you view it as is as a point modulo the action of GL1. So GL1 is right. We'll get there. That's the whole point. So this is a point mod GL1, and so GL1 you see is a sheaf of the spaces are actually group-like spaces, H spaces. There's a product on the spaces itself given by multiplying units. Okay, so they're you can think of them as H spaces, although here you probably want to use something a little bit more complicated. But so I can take a point mod GL1, and so what the idea here is I have this following atlas star mapping to BGL1, and if I map spec R into here, then up here, what do I actually get? Let's map spec K into here, and the point is spec K. So then I get GL1 again. And this morphism is smooth. And so this is, in fact, a smooth one geometric stack. So there are different ways of defining it. You can take kind of the homotopy quotient, the homotopy theory, the homotopy theoretic GL1 orbits. Or what you could do is you could take the usual bar construction pointwise for each simplicial commutative ring. That gives you a pre-sheaf, but it's not going to be a sheaf. And then you sheafify. So R maps to this. And if you sheafify this, you get BGL1.
Sorry. Before, your definition of sheaves, were you in topological spaces, groupoid sets, whatever you want? What is it?
The infinity category of spaces.
Okay.
So what I've been writing S script.
Yeah.
But you can model as simplicial sets.
So for this particular GL1, though, S truncated at 1 is good enough. Because it's groupoids.
No. Let's see, where did that board go? Is it right here? No, GL1 is definitely not. So if I
I meant EGL1.
So again, if I put in a general, it's not a groupoid. If I put it in an ordinary commutative ring, then I get a groupoid out. But part of the point is if I put in a general simplicial commutative ring, then I have lots of higher homotopy groups still in the picture. And we're going to focus Monday's lecture on sort of teasing out the differences between these different constructions. These are derived stacks. So I'll make another comment on that. I was going to talk quite a bit about the difference between higher and derived stacks on Monday, but let me just say now, derived stacks are these sheaves on simplicial commutative rings, or derived, and higher stacks are going to be sheaves of spaces, but on ordinary affine schemes. And that's kind of the difference between these derived and higher. And a lot of the sort of flavor of the subject is finding good derived enhancements of given moduli spaces that you care about that are already defined for ordinary commutative rings. So we'll see that in a ton of examples next time. So one of the things that you can do here is just repeat this process.
Sorry, can I ask you one more question?
Please.
BGL1 to a Luddite like me is like the stack of invertible sheaves.
Yes?
So is that true here also?
Yes. So I was going to, it's true. This is some kind of Picard stack. I'm going to spend a lot of time on Monday talking about that specific example. So for now, what I want to emphasize is that I can just keep repeating this in this world. Since I'm taking sheaves of spaces instead of just sheaves of sets or groupoids, there's nothing to stop me from continuing to push the homotopy groups up. And so I can take sort of star mod BGL1. And this is what I should have wrote before, the classifying stack of BGL1. And now this classifies something like gerbs. This is going to be some classifying stack of something that looks classically like GM gerbs. And once again, what happens is, let's just do the pullback. I'll write this B squared. So once again, I take the homotopy sort of quotient of the trivial action on a point, or I can do this sheafification thing again. So for each R, I take the Picard stack, and then I apply the bar construction to that. That gives me a new pre-sheaf of spaces, and I sheafify. So I can pull back, and if I pull back here, I get BGL1. And then let's prove that this is geometric. So here, this has a map here. So I want to say that this is 2 geometric over spec K. And so here, well, I see that this atlas has fibers given by GL1. So those are smooth. So we see that this is also a smooth, but now it's 2 geometric derived stack. Okay, so we'll explore these examples in a lot of detail on Monday. let me just state one theorem that is why I'm talking about all of this to begin with. So, oh man. The question is, why is this map smooth and surjective and one geometric? Well, because that's kind of what we just did here. So what we need to prove, so if we take the fibers of this map are GL1s, which is a smooth affine scheme. Okay? So that means that this is one geometric. If you trace out the definition, the surjectivity is because, basically locally, line bundles are trivial. Okay, so that tells us surjectivity. So, yeah. So, okay, so I'll just write this. So a geometric stack, geometric derived stack, let's call it M, is one which is a union of some mi's, where each mi into mj is a monomorphism, and each mi is n-geometric for some n. Yeah, some filtered thing. I mean, in this case, it can just be the, n or something like that. Okay. And so what a monomorphism means is that when I evaluate this on R into MJR, this is just an inclusion of some connected components of the topological spaces. Okay. No, I was going to say this. Okay, so this inclusion of some connected components. And so this is just what it's going to mean. So this is going to be the kind of thing that a lot of the stacks that come up are geometric, but they're only n-geometric locally. So then they have different strata that are higher and higher geometric. And so, yeah, maybe now is a good time to stop instead of trying to state the next theorem, I think. Otherwise, I'll go way over time. So I'll stop now. Yeah? Yeah.
Is there any need to use any finer topologies at any point?
So the question is whether there are times where you need to use finer topologies than at all. I mean, sometimes it's very helpful to, I mean, so there's this theorem of Artin that says that kind of like if you do FPPF stacks instead of smooth stacks, then you get the same class of geometric objects. And Toen proved a similar theorem here. So if we had done this if we had done this geometric sort of induction where we asked for FPPF sheaves that had FPPF atlases instead of smooth atlases, it turns out you get the same class of geometric objects. And sometimes that's helpful for proving geometricity results, especially for something like I don't know, for like B mu P, the classifying stack of mu P torsors in characteristic P, which isn't so obvious how to give that an étale cover. Yeah.
So I'd like to understand how this formalism will help me with, say, self-intersecting a curve on the surface.
Okay.
So I imagine that if I do this self-intersection, then the first homotopy group will be just normal bundle or dual?
Well, I guess it's just tor1 of oh, I mean, if you have,
I mean, I should have more information than just the for one. And the question is, what else does this give me in addition?
well, I guess, I mean, is your surface smooth?
Let's say an exceptional divisor intersected with itself on a smooth surface.
Okay. Well, I mean, I guess it also tells you that there's some kind of derived scheme structure on that self-intersection locus. But, yeah, I'm not sure what, yeah.
Because the question was, how much more information can you extract? Because it's about scheme.
Yeah, I mean, okay, so, yeah, okay, so one thing that one might say is that the derived self-intersection might have better deformation theory than the actual intersection, right? It might have, one of these perfect obstruction theories of, like, Fonsecchi and Biran, I guess. And so, and from that perspective, it might behave better for deformations. That's perhaps one answer.
If not, let's break, resume at 2 o'clock, and let's thank Matt.
Thank you.